the ordered space of configurations at k points in X, so it's k tuples that are all distinct. And often I'm going to be more interested in the space that I get after the quotient of sigma k, the unordered configuration space. And I'm going to call that bk of X, B for grade. So what I'm interested in, the goal, is to try to understand the homology of these spaces. That's what I'm interested in. So for example, if X is a graph, then bk of X is a k pi 1 classifying space for the k graph greater root of X. That's a theorem of Everett-Rice. So in this case, we're studying the group homology of these graph greater roots. Okay, so I'm also often going to lump these spaces together. So I'm going to often take the disjoint union over all k and call that B of X. And think of it as kind of a graded space. And so I can kind of talk about all the configuration spaces at once. And I'd like to point out about this functor B that it sends disjoint union to Cartesian product. All that says is that if I have 5 points in a disjoint union, then either 2 of them are in one part and 3 are in the other part, or 1 is in one part and 4 in the other part, that kind of thing. So what that means is that I'm interested in studying the homology of that space and remembering the bigrading. That's all. Okay. So let me give you a little motivation for the way that I want to think about this problem, which is by gluing. So if M is a manifold, M is X here, and I can glue M together from smaller pieces. So let's say I have this kind of decomposition where this left piece I'll call M1, this right piece I'll call M2, and this middle piece I'll call M0 times R. I have some codimension 1 submanifold, and I'm gluing together along a collar like this. Then it turns out that the singular chains on the configuration spaces of the big manifold can be recovered from the singular chains on the configuration spaces in the pieces. So the precise way of recovery takes a little bit of explanation. Because of this property that disjoint union is sent to Cartesian product, and because I'm gluing along this collar, this has the consequence that singular chains on configurations on the collar becomes an associative algebra up to homotopy. And the left-hand side becomes a module over that associative algebra, and the right-hand side also becomes a module. And so I can recover the singular chains of the full configuration space as singular chains on configurations on the left, tensored with singular chains on configurations on the right, over singular chains, configurations in the middle, in the dry sense, of course. So this is a consequence of the theory of factorization homology due to David Ayala and John Francis and others. Okay, so I'd like to adopt this kind of approach to a more general setting than just manifolds. I'd like to break things apart and compute in a local to global fashion. And the big problem with this result, it looks great, right? I mean, it looks like myriad-torus. How many results have been proven with myriad-torus? That's like a basic workhorse computational result. Well, the problem is that this is really hard to compute. Who can compute a derived tensor product of singular chains over singular chains? I mean, that's some huge, hugely infinite dimensional object, and it's difficult to understand. So what one would want to do is kind of approximate, introduce some more discrete approximation to those algebras and modules, and try to work with that instead. So let me talk a little bit about discrete approximation. So let's say that X is a CW complex. As a cell structure, then unfortunately the configuration space doesn't get a cell structure because it's some open subset of the k-fold Cartesian product. But there is an approximation to what would be the cell structure. So we're going to write comp K with a box. This is going to be a subcomplex of X to the K. And it's just the union of all of the cells in X to the K that lie entirely inside of the configuration space. So no cell is allowed to intersect the fat diagonal.
These are open cells.
These are closed cells.
Closed cells.
Closed cells. So this is some kind of, I mean, obviously by definition, this space maps to the configuration space, and it's some kind of discretized approximation to the thing. And it may not have the right homotopy type. So, for example, theorem of Abrams, and I should say that this whole approach, this whole idea with this discrete approximation is due to Aaron Abrams and his thesis. So if X is a graph that's sufficiently subdivided, meaning I just add enough bivalent vertices to the edges of the graph, then the map from the discretized configuration space to the configuration space that we care about is a homotopy equivalence. So we can study the configuration space, all of its homotopical properties, from this discrete model. Which is great. So a big advantage of this is that now we can use discrete Moores theory on this cell complex. The cells of this have a very explicit description as just lists of cells in the graph. Cells in graphs are either 0 or 1-dimensional, and so there's not a lot of complicated stuff going on. So you can really kind of get your hands on discrete Moores theoretical information about.
I'm just not aware of the terminology. Why do we call it discrete? I mean, it's not discrete. Combinatorial?
Well, I guess combinatorial Moores theory might be an alternate phrase. It's certainly not Moores theory. It doesn't come from a.
Right. No. The Moores theory I understand, but the discrete. Why do we call the cell a discrete model?
Discrete. Oh.
It's not really discrete.
I suppose, yes, that's fair. Combinatorial model. That's fair. Yeah. Okay, and so anyway, this is the starting point for a lot of work, previous work on the homology of these breakers. The disadvantage is that, well, this theorem only holds for graphs, and so it relies crucially on the fact that the higher homotopy groups, as I mentioned, configuration spaces of a graph are 0. And certainly general configuration spaces aren't k pi 1s. And the other disadvantage is that it's, because it's a more combinatorial thing, it's not sort of contained continuous enough to do the sort of homotopical manipulations that one would need to do in order to talk about it in this a la factorization homology way. I never wrote the problem, I just said the problem. Oh well. Okay. So those are some disadvantages. And one would like to be able to kind of find a middle ground between the two places that combines both of their advantages with none of the disadvantages. Okay, so let me write SD of X for the partially ordered set of subdivisions of X. I have a CW complex, I can just cut up the cells into smaller pieces and call that a subdivision of X. And that's a partially ordered set under refinement of subdivisions. So if I had such a thing, which I'll write as a map from X to the Moore subdivided space, it's a homeomorphism of spaces. Here's an element of this partially ordered set, then I get a map from the combinatorial configuration space of X to the one for X prime. And this map is it's not a subdivision, it's the composite of first a subdivision and then an embedding as a subcomplex. Okay. And the same method, a proof of Abrams' theorem, which I haven't mentioned, but you might be able to imagine, shows that if I is a subclose set of subdivisions that is filtered and if I look at the limit over the subdivisions in this poset of the maximum over the cells in that subdivision of the diameter of the cell in some metric, if I can choose a metric so that that limit is 0, then I recover the configuration space of X as the colimit over the elements of this poset of the discrete, the combinatorial approximations. The map, there's an obvious map from the colimit of these spaces. And what's it?
Is a homotopy colimit or just a colimit of CW complex?
In this case, the homotopy colimit and the colimit coincide.
So in Ambros's theorem, I mean, this is what he really proves. It's this statement. I mean, the fact when you say it's officially subdivided, you secretly was.
Yeah. Right. So what he shows is that if you want to realize any particular element in homotopy, what you need to do is subdivide a certain amount.
Right.
And because
it's a graph, then
you only need pi1, then you can stop at some point. But you can't stop in general. That's exactly right. Okay, so the idea is to view the left-hand side of this equivalence as an object in its own right that sits somewhere in between the more combinatorial world and the more continuous world that hopefully will have features of both that we can work with. So this brings me to the subdivisional spaces of the title, so let me tell you something about that. So the subdivisional spaces I'm going to write CX superscript ST for the category whose objects are finite W complexes and whose morphisms are the kind of morphism that we saw over there. First, subdivide, and then embed. These are not subdivisional spaces, so let me define what subdivisional spaces are. A subdivisional space is a functor, call it X. I think X is going to get overused in this talk, and I apologize. From I to this category of CW complexes and these particular morphisms, where I is a filtered category. So there's a category of subdivisional spaces, which I'll write M as D for M for embedding. All of the morphisms in this category look like embeddings. What is this category? It's just the category of end objects in CXST. Which is to say, the objects are this, and the morphisms are something that aren't going to be particularly important. If you already know what end objects are, that's great, and if not, it's not so important for the rest of the talk. Okay. Subdivisional spaces give you ordinary spaces. So if we have a spatial realization functor, which I'll write as an imitation of the geometric realization of a simplicial set. And this is just defined to be the colimit over the category I and the values of the functor. That extends to a functor from this category to topological spaces. Okay, so what are some examples of subdivisional spaces? Well, any finite CW complex determines a subdivisional space, but it determines lots of different subdivisional spaces. So I could take an object of this category and index it on the one element category that's just the identity. That's a filtered subcategory of subdivisions. That's not so interesting. Here's a more interesting object. So if I take the partial ordered set of generalized barycentric subdivisions, of the CW complex, this we'll call CW complex Y. This gives a subdivisional space with realization homeomorphic to Y, of course. Okay. What else? What else do we have? We have. Do I have an hour? Or,
yeah. Well, yeah. The barycentric subdivisions are as deep as you want them to be. I mean, you don't put a bound on the depth.
Yeah. As deep as you want.
Yeah.
So we have subdivisional configuration spaces. Which, if I start with a subdivisional space X, which is indexed on I, then we saw earlier that the functor, the combinatorial approximation to the unordered configuration space is functorial for this kind of morphism. And so I can just compose with that functor to get a new subdivisional space, which is the composite, and call this BKSD, subdivisional configuration space. What else do we have? We have a natural notion of homology for these things. Subdivisional chains, which I'll write CSD of X. And what's that? It's just the colimit over the indexing category of cellular chains on the values of the functor. C here is just cellular chains. Okay. Great, so we have kind of all of the pieces that we need to do what we want. And now, what we really need to get going is some Morse theory. So let me talk a little bit about how to do Morse theory in this context. Let me say a little bit about discrete Morse theory. So if V is a chain complex, then a discrete flow on V is a chain map. Let's call it F from V to itself that should satisfy two properties. First of all, it should be chain homotopic to the identity on V. And second, it should be eventually stationary on each element of V. So for all X in V, if I iterate F enough times on X, then eventually I stop getting new things. Doesn't need to pick it somewhere. Okay. That's a discrete flow. If I have such a thing, then I can associate to it its Morse complex. The Morse complex of the pair E and F is, I'll call I of V comma F, I for invariant. And it's just the subcomplex of F invariant chains. So it's the chains in V such that F leaves them undisturbed. And so we clearly, by the eventually stationary assumption, we have a well-defined map F infinity, which is just F of R for whichever R is appropriate. And that forms a chain map, F infinity from V to the Morse complex. And that map is a quasi-isomorphism by assumption 1. Okay. So that's the notion of Morse theory for chain complexes that I'm going to want. The example that you should think I'm going to be plugging into that is V being cellular chains on a space. But now we need a notion of functoriality for this discrete Morse theory. So let's have a chain map, call it phi, and it goes from chain complex V, which happens to be equipped with the discrete flow F, to another chain complex W, which is equipped with the discrete flow G. And I'll say that this chain map is flow compatible if the result of phi after the flow in V is the same, the result of the flow in W following phi following the flow in V is the same as the result of the flow in V following phi. What is this saying? It's saying that this maybe is not, there are a number of different options that you might dream up given this definition for what it means to be compatible with it. This is saying that kind of the flow in V is subordinate to the flow in G. Like it doesn't matter if I flow in V first, G's flow, G sort of encompasses that already. This is weaker than a lot of notions that you would come up with, but it's exactly what you need to make I into a functor. If you write down, anyway, it's exactly what you need to turn I into a functor. So we get a category which I'll call flow sub Z, which is just the category of chain complexes over Z with discrete flows. And there's a functor, as I said, called I to chain complexes. And well, we also have a forgetful functor, which takes a chain complex with a discrete flow and just gives you back the chain complex. And there's a natural transformation, which component-wise is F infinity, which is a quasi-isomorphism.
This statement that this is exactly what you need to make it into a functor, was it a precise statement? Is it a universal property?
Oh, no, I wouldn't want to assert that. It's possible that you could formulate it that way. What I meant was that...
No, I understood what you meant. You meant that it is a functor once you localize
Yeah.
this, but
that's an interesting question. Okay. Okay, so finally, let me define subdivisional flow on a subdivision space X. It's what you might guess it is. It's just a lift of the functor which first uses X to get a CW complex and then uses cellular chains to get a chain complex. And I want a lift of that functor along the forgetful functor from the flow category. So what does that say? It just says that for every space, for every component of the subdivisional space, I should have a flow, and each of those subdivisions should be compatible with the flow. Okay. Okay, so now, oh, I'm going a little fast. Are there any questions? So now I'd like to state the main result. I should have said at the very beginning, I wrote it, but I didn't say it out loud, but this is joint work with Gunny An and Gabriel Drummond-Cole. So some of the, I'm not going to state this in full precision because it would take some time to define some of the terms. So I'll state it nearly precisely. Given the decomposition, of the finite Scuddy complex I started with as x1 alluded to x2 over a bridge, as in the picture with the manifolds that we saw earlier. And given also the data of suitably compatible subdivisional flows. This is where I'm not stating precisely to say what that means, would take some time, on the subdivisional configuration spaces of x1, x2, and the bridge, x0 times I. There's a quasi-isomorphism from the subdivisional chains on the full configuration space. And I should have said, when I introduced it, and maybe it was obvious to you, that subdivisional chains computes the homology of the space. So this is really computing the homology of the configuration spaces of X as we wanted. This is quasi-isomorphic to the derived tensor product of the Morse complexes.
What is the structure of the Morse complex of the bridge?
That's right. So that is hidden in the compatibility. One of the pieces of compatibility that I want is I want for any, so I'll say it in words. Actually, I want the flows not to just be defined on the configuration spaces of the pieces, but also on the configuration spaces of shrinkings of the pieces along the bridge. And then I want for an inclusion that looks like a small interval into a bigger interval, I want that actually to be an isomorphism on the Morse complex.
I see. So the Morse complex will be
an
algebra on the nose.
It is an associative algebra, yes.
And the guys will be automatically modules
yes, that's
on the
right.
nose.
It's entirely possible, it's entirely likely that you could weaken that, but I'm interested in.
But yeah, you want computational
exactly.
models.
Exactly. Yeah, that's an excellent question. Okay. So now, are there any further questions at this point? Now I'd like to tell you about an application. Because you might be thinking, well, okay, fine, you could do this, but to produce a subdivisional flow is a lot of data. I have to have a discrete flow on this infinite list of subdivisions of spaces, and that seems like too much. Like maybe this is a kind of a vacuous theorem because it's impossible to apply. So I'd like to convince you that that's not the case with the example of graphs. So that's like gamma would be a graph with a set of vertices E, a set of edges E, and a set of half edges H. And I want to define a chain complex called S or gamma. And what is it? Well, it's going to be for each vertex of the graph, certain things could happen So either, here's the vertex. It has some half edges coming off of it. Either there's a configuration at the vertex, so I'll put a generator there called V to say that there's a point at the vertex, or there's no configuration at the vertex, so it's a generator called the empty set, or for some half edge coming off of this vertex, there's a one cell that says that a point is allowed to run around on that half edge. So for every half edge in the set of half edges of V, I want a generator. And then to all of those, I want to freely add on a polynomial ring on the edges. And the way I want you to think of this is as populating the edges with points. Okay, so that's a vector space for a abelian group. It's actually bigraded. So bigrading V is 0, 1. It's in degree 0, and this auxiliary grading is like cardinality. So because V represented one point at the vertex, it's in cardinality degree 1. The degree of empty is 0, 0, and the degree of a half edge is 1 because it's like a one cell, and 1 because there's one configuration moving along it. Okay, so that's a bigraded abelian group, and it has a differential D, and the differential is determined by saying that D on that half edge just looks like, let me say that, well, let me call it V of H. So every half edge has a vertex associated to it. Okay, this is just what you expect it to be. Here's H, here's V, and here's a point on the edge, E. So D on that one cell is just the difference of the corresponding 0 cells. Okay. And that's it. That's acid gamma. And the theorem is that there's a natural isomorphism of bigraded abelian groups between the homology of the configuration spaces of the graph and the homology of S, as you might have guessed. Okay, so let me...
That's remarkably explicit. This wasn't known before?
We think it wasn't known before.
Wow.
It's, yeah. Previous approaches have all, as far as we have seen, involved choices. For example, choose a spanning tree in the graph, and then choose a root for the spanning tree, and then a cyclic ordering at each vertex or something like that, and then kind of direct traffic according to that cyclic ordering, allow points to pass each other if they come before each other in the cyclic ordering. So
but that's only going to detect certain chains, it's not going to detect everything.
Sorry?
This type of considerations there, I mean, only for very special graphs they'll give you the full configuration space knowledge.
Well, I mean, so a lot has been able to be done with those kinds of methods, but none of them are describable just in terms of the intrinsic data of the graph. They're all asymmetrical in some sense. Okay, so what's the proof? I'll just sketch it for you. We're going to apply the previous theorem which I conveniently just erased, with x is gamma, as you might have guessed, and then there's supposed to be some decomposition of gamma into two pieces glued along a bridge. So we're going to take the left-hand piece of gamma to be the complement in gamma of the middle of each edge. And we're going to glue along gamma 0 times an interval where gamma 0 is a set that is the size twice the number of edges. So let me see if I can draw a picture. So let's say I'm looking at this graph. That's gamma. Let me do a different graph. Let's say I'm looking at let's do a very simple graph. Let's just do one that looks like that. That's gamma. So then to get gamma 1, I'm supposed to punch out the middle of each edge. So that's something that looks like this. Gamma 2 is going to be kind of the middle of each edge overlapping a little bit. And then gamma 0 is going to look like two intersection points for each edge. Okay, so that tells you what the decomposition is. Another part of the input data for the theorem was the flow. So how does the flow work? So I have to prescribe it on pieces that all look like disjoint unions of corollas of some arity. So things that all look like kind of cones, like that. Let me move this over here. So when I have something that looks like that, what I want to do is I want to think of the vertex as being at the top and allowing configurations to slide down the edges. And that determines the flow. Of course, you could write down an actual discrete flow in the chain complex that realizes this, but that's what's going on geometrically. You can compute the Morse complex of this thing, and locally on the pieces, it looks exactly like this. And then you use the theorem to tensor them all together, and you get S. So let me nearly done. Let me just point out some features, and then give a sample computation, and I'll be done. So what are some features of the model? There were no choices involved. It's functorial for inclusions of graphs. It's very small, so one can actually do computations. There's this, I just erased it. There's this lovely action of the polynomial ring on the edges, which corresponds geometrically to adding points onto the edges. And it decomposes in the same way that the graph decomposes. So here's the proposition. Let's fix a vertex V and write gamma V for the complement of the vertex. And then there's a short exact sequence of Z adjoint edges modules. Let me get this right. In the middle is the thing that computes the configuration spaces of the large graph. Over here is one copy of the punctured graph, direct sum, another copy with a shift. I'll put curly braces 1 to mean that I've shifted the cardinality grading of 1. And then over here is a direct sum over the half edges that live at the vertex that I deleted of copies of the complex for the deleted graph, with now a shift in homological degree by 1 and in cardinality degree by 1. So there's a short exact sequence of chain complexes, and so there's a long exact sequence of homology, and you can do all sorts of computations with this. So you just write a corollary. So the gamma is trivalent. Then we can compute the top homology of the configuration spaces, the homology of degree number of vertices, the configuration spaces of gamma. And what we get is that it's freely generated over the edges by a single class beta. Beta is explicit, but I won't tell you what it is. It's some class in the degree V homology of the configuration space of 2 points in gamma. So that's the kind of computation that you can do, and that's a very, I won't take you through it unless you ask me to, but it's a, you can imagine that since you're computing homology of degree the size of number of vertices, then there's an inductive argument that involves removing vertices from the graph. But
why is that the top homology? Why isn't there homology in every degree?
Sorry?
Why is
that the top homology?
Yeah.
I think that should follow from the theorem that says that the homology is computed by S. I think S is just 0 above degree number of vertices. Yes, in fact, I erased it now, but the only positive degree generators were the things that corresponded to the half edges. And there can be at most one of those at each vertex. So, okay, I think I will stop there. Thanks.
Okay. Thank you.
Any questions?
So, to what extent will this discrete Moores law work? I mean, first of all, you can try to do this in higher dimensions for CW, for your decompositions by using barycentric subdivisions, and so then you can try to take some dilation flow on the piecewise cells.
I hope so. This is rather new, and the only case that we've thought about carefully is graphs, but it's definitely our hope that it will be useful for higher dimensional things. One good thing about it is that there's some flexibility about which poset of subdivisions we index over. So if the geometry says that barycentric is useful, then we can use that. If the geometry says that dividing things into grids is useful, then we can use that. So there's a lot of flexibility built in.
Is there a quantifiable relationship between this combinatorial model for the configuration space homology and the factorization homology of the original space?
That's a good question. Certainly there is.
There should be at least a mark in one direction. Probably from the configuration space 1 to the factorization 1.
I guess I'll say that I think it's likely. That seems likely. Certainly, everything here was inspired by Divisional John Francis and Hiro Tanaka's work on factorization homology for stratified spaces. So this was graphs being the simplest example of stratified spaces that aren't manifolds. So certainly it seems likely that there's a connection. Our emphasis is more on the computations, so we went in a different direction.
What about persistent homology? Can you say anything?
That's a great question. I don't know. I would like to.
But somehow your machinery is completely set up to, instead of taking ordinary chain complexes, take persistent ones.
Yeah, I think that's a great question. I would like to know more about that.
Why would one expect that kind of result, that like you come as trivial and the homology is generated by one guy?
So where trivalent comes in is locally on a trivalent graph. What I'm looking at is something that looks like that, or maybe kind of a lollipop shape. And you can compute H1 of V2, 1 because the number of vertices is 1 in this case. H1 of the second configuration space is one-dimensional on a very explicit class. And you can also show that the homology of the configuration space of the larger graph is kind of generated by inclusions of, or that H1 is generated by inclusions of such things. And then you might think that, so that tells you what beta is. Beta is what you get when you take each of those classes at each vertex and tensor them all together. So that's one thing that you might find as a piece of plausibility for this. Another is that stability phenomenon are everywhere in configuration spaces, homological stability phenomenon. So this is sort of saying that in HV there's really only one interesting class, and everything else is generated in a homologically stable kind of way by adding points, which is something that's well known for manifolds.
Does your Marguerite theorem give a different proof of the Yao-Francis theorem? If you use some kind of cellular approximation, can you concoct your flaws so that you can actually give a different proof of the manifold case?
Maybe.
You need some kind of stronger version of the cellular approximation theorem with flaws. Do they use Morse theory techniques to prove their theorem?
No, I don't think so.
No.
Except, I think they use that manifolds admit handle decompositions, but that's in the background. It's under the hood. No, I don't think they explicitly use Morse theory at all. Yeah, I don't know. That's another interesting question. I don't know the answer.
What is the theorem? Sorry.
Well, he started with the Marguerite sequence for configuration spaces of manifolds, where you have a manifold, you break it into a neck into pieces, and you get it, you get the tensor product of the two things. And then he proved it for his cellular decompositions of CW complexes. But he had a condition that he needs these discrete Morse laws on each piece, which are tightly aligned with the decomposition. So the question is, if you use the cellular approximation theorem applied to manifolds, can you find the flaws so that everything works and you get a new proof of the theorem? It looks like...
I could imagine that if you take kind of a flow in the bridge that only does things in the interval direction and kind of doesn't do anything to the cross section, that then you might be able to. It seems plausible.
The other thing is there is this non-commutative Poincare duality of Ayala and Francis.
Yeah.
And can you use this type of models to, for example, it should work for PL manifolds, right? And not just
Right.
for, yeah.
Yeah.
And I don't think that proof works. It only works for.
I believe that's true, yeah.
So somehow this technique should probably.
Yeah.
These guys, PL will certainly give you your several
Yeah, and,
subdivision spaces. So.
on the subject of non-abelian operatorability and mapping spaces, you know, another question you could ask is, can we arrive at computational models for mapping spaces using this kind of, I don't know, I think that's an interesting direction to go in.
Thank you.